I'm pleased to be here, kicking off day 2 of Scala by the Bay. And I thank you all for being here today. And I'm very thrilled that Alexi had me here. I'm going to be a little bit of a misfit, though, because Alexi promised that I would be giving a talk about AI. But I'm actually going to be talking about a primeval dilemma facing every single human being on Earth. And that is the trade-off between exploration and exploitation. So I've been a software engineer for the past 15 years, and I can tell you that I've come to rely increasingly on my past experience to guide my choices. So choices about tools, languages, choices about design and architecture, and just about every aspect of software development. But there's a little bit of a tension here. And that is that we work in a fast-moving field. The ecosystem changes underneath us, year to year, month to month, and even week to week. And so in order to stay relevant, we need to explore. But this takes time that we usually don't have. And when we explore new technologies, we don't know at the beginning what kind of value we're going to get out of it. And so when you compare that to fixing bugs, where the value is well known, you often make the choice to fix the bugs. So today I'm going to be telling you a very personal story about my company, where we faced this very dilemma. In our case, we either needed to explore or go do something else. So we're a Scala shop, unsurprisingly. And I should warn you that throughout this presentation, Scala isn't really the main character. It plays a supporting role. And I hope that the takeaway message here is that although Scala's gotten a lot of attention for being a scalable language, building all kinds of wonderful applications with it, you can also take it with you into unknown territory. When I say unknown, I don't mean something that no human has ever explored, but something unknown to you. So let me tell you the story. It's going to come in several chapters, starting with our founding. So we got started in 2014, and the founding team included myself, Greg Orzel, and Christian Kaiser. So we got to know each other at Netflix, and we worked in another startup together. And over time, we kind of decided, hey, let's pool our expertise together into a new venture. Why not do that? And so we co-founded Order of Magnitude Labs, and we needed to first figure out what it was we were actually doing. So we quickly decided on the frontier that we were going to be exploring, and I'm calling this intelligent machines. Notice I'm not using the word AI here. AI is kind of an easy term to use, but unfortunately it means different things to different people. So when I say intelligent machines, I actually mean machines that can learn how to perform a multitude of tasks that most life forms find pretty easy, but today's machine learning and reinforcement learning techniques find to be very hard. So ironically, one of these things is trading off exploration and exploitation. It's really hard to get machine learning and reinforcement learning algorithms today to explore at the right time. And so when we talk about exploration, this is key to really building a model of the world that allows the agent to learn a variety of tasks. You know, tasks that might be as simple as foraging for food, as simple as locomotion, communication, right? All of these things. So our hypothesis was and still is that there is a single algorithm that implements this learning. And we wanted to go find it. In fact, we had read enough that we felt confident that the nuggets were out there and that we could then apply engineering to it. So here was our initial business hypothesis. You know, the emerging approaches are there. We need to read the literature, look at what's out there. Then we need to use our engineering background and apply that. And then here comes scale, and now we've got some amazing problem solved that has real value in the market. So we set to work building a prototype. And guess what? We chose Scala. So aside from all the usual reasons you might expect that Scala is great, we also thought that since we had experience seeing it at scale, we knew we could take it from a prototype all the way up to a production application. So we started working on our first prototype. And I got very excited because I had used Akka before, and what we were building was kind of a neural net of sorts. And what better model to create an asynchronous distributed neural net than Akka? So you can imagine a single actor would be kind of like a unit or a neuron, and the messages being passed were kind of like these synaptic connections. So I built the prototype, and it didn't work. So here was the problem. I had already developed scalable applications in Scala, so I could see what you could do at scale. And that kind of distracted me a bit. I went and built the fancy version of the future before understanding the basics of what I was doing. What is the domain that I'm working in, and what is the problem space? So the first lesson was just because you can do something doesn't mean you should when you're starting out. So then we went and built another prototype. This was the embarrassingly simple version. Instead of a car with kind of weird bells and whistles, it's this little bike. It doesn't have pedals. It doesn't have brakes or any of those fancy things. So this was embarrassingly simple in that all it was really was a set of case classes and some pure functions, and these were all being stuck together. I actually presented a scaled down version of this prototype at Scala Days in 2015. So if you're interested, the link's up there, it'll be in the slides. So we built this prototype, and it kind of worked, but it didn't really work. And we kind of learned that there were some basic holes in the fundamentals of what we were building. So we went back to the research, and we couldn't answer these questions. We couldn't fill these holes. And it started to dawn on us that the landscape looks more like this, that we thought we could climb this mountain and build this thing and apply engineering to it. But in reality, if we're going to hold this hypothesis that yes, there is one algorithm, we're not on the right mountain range. So we now needed to decide whether we were going to explore or go do something else. So we're at a crossroads. We all each had to do our own soul searching. And Greg, being a very reasonable person, decided, you know, this is not what I signed up for. So he went off to do other things. And Christian, on the other hand, was very enthusiastic about this problem space, wanted to give it another shot. And I did a little bit of thinking about it, and I kind of realized something about myself, which is that as a kid, I was actually the one on the right. I was really into art and music and all kinds of wonderful things. But as I became an adult, I was more like the kid on the left. So I kind of knew that somewhere deep down, there was this artist person that somehow got buried over the course of, daily life. And so aside from seeing the potential value in solving this problem, I also kind of had a personal goal, which was I wanted to get back in touch with that artist and kind of have this blend of engineering and art come together. Okay, so little did I know that we would later stumble upon this amazing formula. So don't be scared, don't worry about understanding the formula. But what I want to tell you about it is that this is essentially the value function that we believe all life forms must optimize in choosing behavior, in choosing policies or a course of action. And so the takeaway message is there's two terms in this formula. One relates to exploitation, and the other one relates to exploration. And so we all have that creative explorer inside of us, and we need to get in touch with that person to do these kind of things. So exploring is really hard. And why do we not do it? Why is it so hard? Well, the more experience you have in life, the more sophisticated your model of the world becomes, and the better able you are to predict a course of action that will lead you to valuable outcomes. So if you know how to achieve your goal, how to fix that bug, how to build that service, there's very little incentive for you to go investigate 10 other ways that you might do that. So how do we push the teeter-totter in the other direction? Well, we have to convince ourselves that the knowledge that we hold today, the information that we have, the model of the world that we have, is inferior to what we will have in the future after we do that exploration. And that's hard because we don't know how good our model will be. We just know that there's some uncertainty that we need to resolve. So I needed to kind of relearn how to explore, something that I probably did really well as a kid. And my first take at solving this problem was, let's apply engineering best practices, because if you have a problem, there's nothing like engineering to solve that problem. Why wouldn't you have one single code base? And why wouldn't you have code reviews, right? Why wouldn't you want to get rid of dead code, have a project plan and a spec? These are all wonderful things. So I kind of started out with this mindset. But in the end, these things were not getting me the results I was expecting. So I realized I was optimizing for something that was no longer relevant in my current context. I was optimizing for getting code from a developer's laptop into production in a manner that was low friction, low risk, and minimizing technical debt, doing continuous deployments, right? This is what I was optimizing for. But at the end of the day, in this world, the stuff doesn't matter. So what I should have optimized for was formulating hypotheses and testing them and rejecting the bad ones. This is the cycle, hypothesis testing, where the friction needs to be removed. And I was actually adding friction by trying to do these engineering type behaviors. So I learned a few lessons after a lot longer than I care to admit about hypothesis testing. So I want to just take you through each one of these in turn. So the first one, interestingly enough, is you need to be able to contradict yourself. What do I mean by that? Well, I can remember having technical discussions with Christian, and let's say it was on a Tuesday, he would make a statement that was directly contradicting something we agreed must be true on Monday. And I felt very disoriented by this. I was as if he was changing the spec. And it wasn't until I really thought about that I realized that I was acting as if what we decided on Monday was the spec. But in fact, we were going on a mission to find the truth. And in trying to find the truth, you will be wrong. And so you need to say things that are directly contradicting what you thought before. So in other words, when you encounter evidence that doesn't match your hypotheses, go get new hypotheses, right? It's like, imagine you're exploring a city, you are unfamiliar with it, you don't even have a GPS or a phone or anything like that. You're hungry. What are you going to do? You're going to form a hypothesis. The hypothesis would be, I think the food is over there. So you drive that way. Then you run into a residential neighborhood, contrary evidence. What are you going to do? Turn around, go another direction. So this is not as easy as you might think. We had a problem where we needed to see what was going on in our experiments. So I took it upon myself to build an application that we could use for all of our experiments to get some insight into. And this slide here is actually the talk that Alexi mentioned, my 2015 talk on Scala.js. So this application, hooked into the experiments, collected some data, and because I was trying to be low-tech, spits it out into JSON, and I had this Akka HTTP server going on with a Scala JS front end and then D3 visualizations, right? So I had this kind of whole pipeline mapped out. So there's nothing wrong with this app, except that it adds friction to the hypothesis testing loop. And the reason is that our hypotheses were not as stable as I had imagined. These experiments were changing more than I anticipated when I built the app. And so different kinds of data came about, and that required a lot of work to integrate a new experiment. And furthermore, new visualizations were needed that I didn't anticipate, so that was more work. So there was friction added, and what this meant was I was afraid of saying I was wrong and rejecting the hypothesis I was testing and trying a new one. So we had to come up with a compromise. How can we get insight into our app, but then still not add this friction? So we came up with this, very low tech. We had some very simple functions that printed out, SVG files and stuck it in an HTML page, and we could load that up. There's no application needed. And this kind of freed us up from this idea that, oh, we had invested too much in the current hypotheses. So the lesson here is the more that you've built, the harder it is to admit you're wrong. So be careful about estimating your uncertainty about your hypotheses and gauge your investment accordingly. Okay, so another way to look at it, what are signs that you're investing too much? When you have to keep adding complexity to prove that you're right, then at that point you should start applying Occam's razor. How many of you guys know what Occam's razor is? Okay, good, most of you. Just for, if you're not familiar with it, Occam's razor is really just this statement that if you're dealing with multiple competing hypotheses, you want to select the hypothesis with the fewest assumptions. So at this point, when you're adding a bunch of complexity, you want to step back and say, what are some other alternative hypotheses that we can use to simplify what we're working with? Okay, so I kind of got over this message of, okay, hypotheses are unstable, I'm going to be wrong, this is not a spec, okay? But now we needed an environment to work in. We like to think about our development environment, our build process, our continuous integration, and all these wonderful things. But guess what? This is not what we're doing here. We need to run experiments. And in order to run experiments, you need a laboratory. So how do we set up our laboratory? First of all, tools are essential. You need to have the right tools, and you need to have enough tools. Because if the only tool you have is a hammer, everything is going to look like a nail. So I have a corollary to that, which is that let's say you add a screwdriver to your toolbox. Now all of a sudden you can tell the difference between a screw and a nail. So I kind of came to realize how important tools are to this whole process. You might already be thinking, yeah, of course, you form hypotheses, you do experiments, you form hypotheses, you do experiments. But you start to learn patterns as you go and realize that you need some tools. And that when you do an experiment, you might add a tool here that then helps you do the next experiment. And furthermore, when you add new tools, you might start seeing the world in a different light. So you might actually realize new hypotheses. I mean, there were several times when we kind of added a tool to our toolbox, and in our case, this is mathematical formulas and techniques. And we realized at that moment, hey, that problem we had a month ago and we couldn't answer that, adding this tool actually helped us see the answer. So how do we think about the toolbox? I think a good way to think about it in this context is that it's really an index for what you know. It's a reminder of the techniques that you're already familiar with, so that when you are going out to solve a new problem, you don't need to go back into first principles and say, hey, what do I know? So when it comes to what should you add to your toolbox, guess what? This is code. Code is cheap. So be greedy. And when you see something that might be applicable at some point, go ahead and add it to the toolbox. This took some time for me to get over because I was used to thinking, well, dead code, it's not being used. This is going to add, friction to the process and people are going to be confused. Not so in this case. You also want to make sure that when you're testing hypotheses, you can be lazy. That the tools are within reach. They make very few assumptions and they're versatile. And then lastly, don't over-engineer them. Going back to the Insight app example, for where we were at, that was over-engineered. So I made my peace with printline. It's okay. So what did we put in our toolbox? We actually, since we're dealing with math, we have a bunch of primitive operations on floating point values, just collections, right? Pretty much untyped. If you guys have ever used Python and NumPy, it's kind of sort of analogous to a mini version of NumPy, right? It's a bunch of functions you can use, but you don't really know what should be used with what. So that's how we started, but eventually we kind of started to be able to name things. And at the time we could name things, hallelujah, we're using Scala. So now we can start adding types. And we can start adding methods to those types and build on top of that. So now the tools come with an instruction booklet. We have types, so the types really make sure we use these tools correctly. So I would say this is kind of a bonus on top of some of the popular scientific languages and frameworks, right? Like MATLAB and Python. Now we have types. Hallelujah. Okay, so we have tools, but we need a workspace to operate in. The tools need to be really accessible. We need to not have a lot of heavyweight process to get going on an experiment. And we need to not have a lot of distractions and keeping the environment going. So we were very lucky in the timing because at this point in time, Ammonite comes out. How many of you guys know what Ammonite is? A lot of you, good. How many of you guys have used it before? Fewer. How many of you use it on a daily basis? Fewer, okay. So I won't talk a lot about all the wonderful things that Ammonite does and all of its features. Howie there, to call you out, has some great talks about it, and I think he's going to be speaking about it right after this. But for us, kind of the big win was we can easily import our toolbox into Ammonite, and we basically use it as a REPL. So there's several different tools within Ammonite. There's a REPL. There's also Scala scripts. So if we wanted to go out and test something like real quick, hey, does this function behave like I thought it would? Or, hey, what happens if I do this? Import your tool, write a line or two of code, and bam, you have the answer. There's no setup involved. If we wanted to do something more involved, let's say repeatable, we can write a Scala script. It's just a plain old text file and run it using Ammonite as a script. Zero setup involved. So the argument in my mind that Scala is too heavyweight or has too much overhead to get going, I think that's actually fading away. And that you can do these quick and dirty things using Scala. So we still have because we're in Scala, we now have the option of adding more process and more weight to it when that makes sense. We can still create an SBT build, and we can still do continuous and integration and all this wonderful stuff. Okay, so now we talked about the basics of exploration, but how do you do it as a group? What if you have more than one person? And the thing that I needed to figure out was, at what level should we be in sync? And my first instinct was, well, we should have one code base and we should do code reviews, and of course, why wouldn't you? But what I kind of came to land on is really, you want the ideas to be merged and in sync, but the code can be forked. It doesn't mean the code is just completely orthogonal, but it means that it doesn't have to, not every single person on the team has to be on the exact same code. So imagine this, right? Think back 150 years before we knew how to build flying machines. Well, there were many different form factors proposed for flying machines. and they were all wrong. There was a lot of ambiguity going on. So there was a number of hypotheses that all seemed equally plausible. Imagine if someone had said, hey guys, this is the form factor we're going to test against. You guys can make your tweaks, but this is where we're going to go against. We never would have created flying machines. So if you require a single code base too quickly, you might actually downplay the level of ambiguity in your environment. You're sending a message to the team, this is how it is. When what you really want is to keep your options open and allow ideas to flourish. The other downside to having a single code base when there's this much ambiguity is the discussions naturally slant towards how to do something. How should the code be structured? What are the coding styles? And this really takes away from the high level of what. Talking about how feels really good because we get a sense that, hey, we know what we're doing, we're just kind of going to figure out how to do it. But if you're making yourself feel good but you're not actually making any progress, that ends up in the long run hurting you. So what should you share? Well, you should share, what do we think the principles of flight might be? What are the hypotheses? You want to share these as a group often and eagerly, because as a group, you can perform very powerful thought experiments that might throw out the worst ones. And the ones that survive this group discussion are then the ones that the group is going to go out and test. You also want to share tools, right? If you think of tools as this index of what you know, well, guess what? You adding a tool to the toolbox now means that the team as a whole has their knowledge enhanced. So you might not think a tool is relevant right away, but your teammate might think, oh my gosh, this is going to solve my problem. And lastly, of course, as they start to emerge, you want to really be in sync on the requirements. The whole process of doing this exploration is getting to the point where you think you could write down the requirements. So that's going to happen slowly over time. So contradict yourself. You're going to be wrong. You need to optimize for hypothesis testing in a laboratory environment, not in a production environment. And let the ideas come together, but don't require the implementation to come together. So just to briefly talk about this, at the end of the day, we want to build a real practical application of value. And we can't get there by exploring. You can't do that for forever. You need to execute. And so we've done several oscillations, I would say, between exploration mode or creative mode and execution mode. So I call these modes because each one of these requires a very different mindset. And you can't really keep that same mindset, both of these at the same time. So we kind of have this loop where we're iterating between sort of taking a step back, being creative, and executing. So we need to have a good algorithm for mode switching, and it's quite simple, I think, but hard. First, you need to know which mode you're in, and then you need to look for signs that it's time to switch. And lastly, you need to give yourself time, because it takes time. So creative mode is what we've been talking about all along. Which mountain should I climb? In this mode, the hypotheses are incredibly volatile. And you're really kind of looking from the 30,000-foot view. Execution mode is more like, I need to climb this mountain. And really for what I've observed is the really only difference between creative and execution mode is how stable the hypotheses are. In order to execute, you must have stable hypotheses because you're looking at the goal and you're trying to get there. So in terms of when should you switch, if you're in execution mode, you need to know when to become creative again. And this goes back to contradicting yourself. You still need to be able to contradict yourself. We just hope that when you're executing, this happens a lot less frequently. So when your assumptions are wrong and you start to encounter this evidence that's contrary, then it's time to change your mode. And so, technical debt and mounting complexity could be a sign that it might be time to go do this. And given the environment we work in, lots of things moving pretty quickly, we should consider doing maybe a mini creative mode pretty often. And then execution mode is a little easier because you kind of naturally want to do this. When you can describe the goal, you think you can get there, and you can't find any counter evidence, that's when you need to go execute. And then the last thing is give yourself time. So this one I don't have an algorithm for, more of a heuristic. And what I've observed is the farther you have to zoom in or out, the longer it's going to take to switch. So if you're going from optimizing bytecode to, let's say, coming up with some kind of 5-year plan, you might need days to switch, or even weeks. If you're fixing a bug and you realize you need to do a refactor, maybe in an hour you can switch. But do recognize that it does take some time. So just kind of to briefly summarize what we talked about, prototyping, build the embarrassingly simple version first. Understand what it is you're building. Don't be tempted by all the wonderful things you know you can do in Scala before you kind of understand what you're doing. Make sure you're optimizing for hypothesis testing. This is not optimizing an assembly line of code, if you will. And then lastly, make sure you're mode switching. So just kind of taking a step back, I'm going to bet that a good part of the reason why you all are here is because you want to explore. You want to explore new technologies, new developments in the ecosystem. And you're probably going to come away excited about all the things that you learned. But what I want to drive home here is that that's step one. This is the beginning of exploring these new things that you're learning about. I hope that I've convinced you that Scala is a great language for just trying things out. You don't need to go into a heavyweight process of setting up a build and setting up a project in order to tinker around. So I encourage you to take some time with what you've learned and what you're going to learn in this conference and start playing with it, and exploring your curiosity. So thank you very much for your attention, and if there's any time, I don't know, then we'll take questions.
Please repeat the question for the recording.
All right. Okay, so back right here.
So there are, that's another interesting topic from in person. There are well-known like upper confidence bound. Can you comment on that?
Sorry, there's well-known.
There are well-known already for exploration, like upper confidence bounds. Can you comment on that?
Sorry.
Upper confidence bound.
Upper confidence bound.
Yes.
In terms of,
Exploration.
you know, so that would be an interesting. So in terms of like actual metrics.
Right.
Yeah, I mean, I didn't sort of bring that in. I think, you know, that's another interesting one to bring in, right? We've been kind of doing this kind of from a feel perspective, from a seat of the pants perspective, but there might be interesting ways to bring in sort of a more regimented approach to kind of knowing, hey, when do you have that tight confidence bound and when should you explore? So thank you for bringing that up.
So I think I understood you correctly. I think you were saying that everybody in this room should fork the Scala compiler and start playing. Is that right?
This was a pitch for you, Miles. So everybody go fork the Scala compiler. Anything else?
Questions? One more question. Thank you very much, Julie.
All right.